Hey guys, can you type names? Can't see if anybody's here yet. Is there anybody out there? Cool. Right, got Alex so far. We've got Fifi, Callum, and Becca, Roddy and Sophie. Anybody else? Caleb, Charlie, Joan, George, Leo, any of you guys there? If anybody else is there and you can't comment for whatever reason, send me a message on Teams. Cool. All right. Who's that again? Is that Joan? I think that is. Is that right, Joan? There's Caleb. Cool. Joan, was that you? Yes, cool. So just missing Charlie, George, and Leo. Cool. All right, let's get started then. So we are officially starting further maths. There's some noise outside. George. Cool. So yeah, today we officially start further maths. With me, you're going to be looking at. I'm just going to shut the window. So with me, we're going to be looking at complex numbers, and with Helen, you're going to be looking at matrices. Yeah, so this is the start. It's going to be quite a slow start. There's some quite challenging new concepts and new topics, so we are going to go quite slowly. But yeah, so complex numbers. Please stop and ask if you need me to go over anything again, because this is kind of brand new stuff to all of you guys. All right, so there's some key skills that we're going to be using in complex numbers that you guys will have seen earlier on in maths. What's the point of them? We'll get to that. It's not really there's a point to them. You could say, well, what's the point of numbers? What's the point of negative numbers or zero or fractions? You know, they exist, so we study them in mathematics. So skills that are gonna come up, or things that might seem familiar, is simplifying surds, vectors. These are very similar to vectors, and also rationalizing denominators. They come up a lot in engineering and mechanics, but we'll get to it. Okay, so yeah, simplifying surds, vectors, rationalizing denominators. Those three topics, some of this is going to seem similar to those topics. So it's all those skills that we're going to be using again. Alright, just need to... where should we start with this? Okay, so the idea is... square rooting and quadratics. This is where the idea kind of comes from. So if we have a quadratic, like a blank quadratic, ax squared plus bx plus c equals 0, You guys all know there's a few ways we can solve it. We can factorize it, we can use the quadratic formula, we can complete the square. So the quadratic equation, quadratic formula says minus b plus or minus the square root b squared minus 4ac all over 2a. And I taught you guys, I think it was me, it might have been Helen, can't remember, or someone at GCSE taught you this thing here we call the discriminant. So b squared minus 4ac is the discriminant, and it tells you how many roots a quadratic has. So we said if b squared minus 4ac is greater than 0, it has 2 real roots. If b squared minus 4ac equals 0, it has 1 real root, or we could say it's kind of 2 repeated roots. And we said if b squared minus 4ac is less than 0, it has no real roots. Okay, and why did it have no real roots? Because we said you can't square root a negative. Alright, so that's not strictly true. And this is the point where we can admit that to you guys. You're mature enough mathematicians that we can say, well, actually, you can square root a negative, and any quadratic will have 2 roots. There might not be real roots, they might be repeated roots, or they might be imaginary roots, or complex roots. But every quadratic will have 2 roots, every cubic will have 3, every quartic will have 4, without fail. So, the whole idea behind complex numbers, and indeed imaginary numbers, is the idea behind square rooting a negative. So I'm just trying to work out order. Let's do some history because we got a bit of time. Yeah, we got some time. So we're going to talk about numbers, where they came from, the history of numerology, which I think is very interesting. So we're going to go way back in time. And we're going to go back to the early humans. So the first bunch of people that had numbers. So early humans, we'll see if we can do a timeline here maybe. I don't actually have the dates, but yeah, we can make it pretty rough. So here's our timeline. And we're going to start way back with early humans. And this is the history of number. What could we call that? That's a nice pun we can come up with, number history. Okay, history of number. So, way back, we had the early humans, and they kind of realized that they needed some numbers. I'm not sure what came first, numbers or language. That's interesting. Oh, probably language, but I don't know if writing or numbers came first. But we needed some numbers. So we came up with the natural, or most of the natural numbers. So I'll do these as sets. So yeah, we'll start off with natural numbers. We didn't have 0, so instead let's say we start with the positive integers. Early humans, we need positive integers. So something better. There's my symbol, the set of numbers, the positive integers. Because we needed numbers for counting things. You know, today I ate 12 antelope. How many did you eat? You know, how many caves have you seen? How many caves have you lived in? I don't know, Stone Age man, Stone Age human, whatever. You needed some numbers. We didn't have negatives. We didn't know what negatives were. That made no sense. We didn't have 0. Just had Z. Okay, so we evolved a bit. We were not evolved, but we we got more sophisticated in our societies, and then the kind of so ancient humans. We got the Egyptians, Babylonians, the Olmecs. They were like, wow, we need some fractions because, we've got half a field of wheat, half a field of maize. We need to talk about this. We need to talk about ratio, how much water we're going to use, how much fertilizer we're going to use, irrigation systems. You got all these new things that we need new numbers for. So we started to bring in rational fractions, basically. So that is the number set Q. But again, we only really had the positives. We didn't have the negatives. So I'll do for Q. Okay, where are we up to next? So we started bringing in, so let's write this down. So we had integers, so positive, integers. Then we had Q, so we needed, basically we're talking positive rational numbers. Okay, where do we get to now? So we also had the idea of zero started, but it wasn't as in zero as in a number zero, it was a placeholder. It was the absence of thing. So we started using zero as a placeholder. But we weren't fully embracing zero properly back in the Egyptian time. Okay, so interestingly enough, meanwhile, over in China, so ancient China, we had zero as a placeholder. We also had negatives over in ancient China, but people don't really talk about it much. So we started having negatives in there as well. So let's put maybe kind of Z. I'm going to put it there. So that's just the full set of negative integers, which gives us the full set of integers there. We've probably got some Q negatives as well. Whatever, They're starting in ancient China bringing in these numbers as well. Okay, the idea of actually using zero as a value, though, as a number, and then actually using negatives properly wasn't for years. So the Greeks and the Romans hated negatives. They didn't use zero, they didn't use negatives. They came up a bit in their mathematics, and they were against it. So say you had an equation, y is minus 2x plus y minus 2x minus 3. They would always write that on one side. They would get rid of the negatives. However they wanted to write equations, they would try and eliminate negatives wherever possible because they didn't want to use them. So Greeks, Romans, again, they had zero as a placeholder, but they didn't like it, and they didn't like using negatives either. So still got no negatives. Anyway, meanwhile, India and Persia, hundreds of years ago, I think like 500 years ago, and Cambodia, weirdly as well, started bringing in the idea of using zero. So we brought zero in, we brought negatives in. So at this stage, we now pretty much have all of our real numbers. So we've got the natural set, so we've got natural numbers, we've got real numbers, we've got our integers. Yeah, so at that point, really, mankind or humankind has discovered number. It's not until a lot more recently. I mean, in Europe, we were totally against it because of the Greeks and the Romans. We were against all of this. It wasn't until a few hundred years ago in Renaissance Europe that we actually embraced zero, negatives, and numbers. So it's kind of this point where we're now happily talking about all these different types of numbers. Now, the last kind of type of number we hadn't discovered, and this was only up till about 200-300 years ago, was complex numbers. So it took right up until that point where we finally kind of finished the mathematical story of number. And complex numbers is what we're talking about just now. It's being able to square root negatives and introduce that whole extra set of things. So, now Gauss from, I told you guys a story about Gauss, I think that was you guys. Gauss was one of the main kind of proponents of complex numbers. What Gauss really believed is that calling them complex or calling them imaginary was a really bad idea. So we're going to come and look at that in a minute. What I want to do next, though, is actually start sketching these and trying to get a bit more to the bottom of this. So guys, I did have a nice Gauss quote, but I can't remember. I think it's on a slide a bit later. Yeah. But the idea behind these is they're just a different type of number. Don't be kind of scared of them. We've got negatives, we've got positives, we've got fractions. We've now got something else called complex numbers or imaginary numbers. All right, so we're going to try and solve a quadratic. This quadratic here. Yeah, okay. So we're going to start by trying to solve this one. Now, the way we're going to solve this is, obviously if I tried sketching this, we would get a, it would be something like this, with a minimum at -1, 4. So you complete the square, you can see where it is. We're going to try and solve this via completing the square with the use of imaginary numbers. So we're going to be looking mainly just at this quadratic today. So x squared plus 2x plus 5 equals 0. So I'm going to complete the square on this, and we're going to get x plus 1 squared, take 1 plus 5 equals 0. So as I said, x plus 1 squared plus 4 equals 0. I'm going to take the 4 to the other side and square root it. And this is the point where before you would have gone, something's gone wrong, and yes, perhaps something did go wrong, perhaps you made a mistake. But in this case, we've made no mistakes, so we're going to try and solve this. So I can basically add take the 1 over, so we get x is -1 plus or minus the square root of -4. So what we're going to do with that is we're going to use surds to pull this apart. So x is -1 plus or minus the square root of -4. The way we're going to deal with this is we're going to pull it apart using surds. So x is -1 plus or minus, well, I can change that into √4 times √-1. √4 we know is 2, so we get x is -1 plus or minus 2 √-1. And what we're going to do is we're going to say the square root of -1 from now on has a value, has a constant. We're going to call it I. So I is the square root of -1. And this came into mathematics, what was his name? I can't remember. Some guy, some mathematician was trying to solve a cubic. He was trying to come up with an equation to solve cubics. And the only way that they could get around solving cubics with their equation is they kept getting the square root of -1, and they needed to kind of deal with this. So they ended up kind of saying, all right, fine, we'll give it a name, we'll call it I. Just use that as a value, work through. And it ended up cancelling out and beautifully solving a cubic equation. And it was that was the kind of first discovery of it. It was later on Gauss kind of looked at it a bit more. And we actually had kind of formalised, we said, okay, there is a separate set of numbers, imaginary numbers, which are all going to be factors of root minus 1. So root minus 1 is, we call it I, is a constant. And on its own, we'd call it an imaginary number. When we combine it, though, with a normal number, a real number, we get a complex number. So I'm going to write that up here. Root minus 1 equals I. So this part here is going to be imaginary. And this part here is real. When we combine an imaginary part and a real part, we get what's called a complex number. Not X, but the rest of them. Cool. Everybody right with that so far? So we've got imaginary numbers are a new type of number. When we combine them with real parts, we've got a complex number. There's a notation for that. So if we had... let's write it up here. So let's just say here, an imaginary number has a factor of square root minus 1 is I. A complex number. We normally use the letter Z for complex numbers, so Z has a real part and an imaginary part. So for example, Z equals A plus BI. The real part, we could notate this as RE of Z. The real part of Z is A, and the imaginary part of Z, IM of Z, is B. And you can never combine those. You can't kind of mix up your real part and your imaginary part. They are separate, two parts of the same complex number. So just right there, we can combine real and imaginary parts. Cool. All right, has anyone got any questions so far? Because this is, new. It's a big concept. Anything you want to ask me at this stage? It will make more sense. I'm going to get GeoGebra up in a minute, and we're going to look into a third dimension. It'll all be all right. But anyone got any questions so far? Right, I'm going to guess. Oh, okay, yeah. Do they always just cancel? What do you mean just cancel? Do they just always cancel? What do you mean there, George? Oh, in a. Do you mean for the two roots of a quadratic? No. Basically, in a cubic where they kind of came from, yeah, they do. In the cubic where they were kind of in the first use of an imaginary number, they ended up getting kind of squared out, and they weren't actually part of the solution. So it was a cubic. They were finding a blank equation, solve any cubic. To prove their equation, they used an imaginary number, which got cancelled out. So it's kind of used as a tool. That's why when it was first used, it wasn't really discovered. It was just, I blagged it, I substituted this weird thing in, and it worked. So it was I think another generation later, so 30, 40 years later, that it actually got formally discovered and used. But yeah, it was used in a proof, just as a throwaway tool, basically, and it wasn't until later that we appreciated how big measuring numbers were. So yeah, that they do it's as real a root, although that's a very bad way of describing it. We'll stick with that, and we'll see if it makes any more sense in the next couple of slides. So we were just looking at solving this equation. So we found that x was -1 plus or minus 2i. Those are my solutions to the quadratics. X is -1 plus 2i, and x is -1 minus 2i. So these are my roots. Right, I'm hoping this isn't going to confuse things more, but we'll see. Because I always think it's nice to be able to picture things. Yeah. All right, so we're going to have a look at GeoGebra. Let's just see if I can bring this up. So GeoGebra coming up. There you go, cool. That's a bit big. Oh my god, very big. Right, so first of all, this doesn't work perfectly. It was I didn't make this. I stole this off the internet, and whoever made it did a bad job. I fixed it as best as I could, but it's still slightly broken. So there's my disclaimer on this one. I just need to make this a little bit smaller so I can see what's going on. So this is going to be awkward. Oh my god. I'm just wondering what the best way around this is, because this looks hideous, doesn't it? View, window tools. GeoGebra is horribly optimized for my computer. Okay, I'm just gonna. What is the best way of doing this? I'm just gonna have a look on YouTube to see how this looks. I'm gonna go full screen and see if it all kind of fits. So if I make that a bit bigger. Hopefully this works. Yeah, bear with me, guys. Okay, let's try going full screen and see how this comes out. Okay, Okay, I've got me back. I'm going to add one more window, and this hopefully will do it now. Sorry guys, I should have tried this before, but where's my second GeoGebra? Yes. All right, that's better, isn't it? Cool. Okay, so I have plotted a quadratic with no roots, as you all can see. Is that kind of displaying properly? We could do that being zoomed out a bit more, I think. So I'm going to zoom this one out here. Oh, because I'm still on YouTube, yeah. Alright, so let's just turn the iPad off. Can I? There you go, cool, right. Now we're talking. Okay, so this one still is a bit rubbish, isn't it? I wouldn't mind zooming in a bit more, but it does not like it when I do that. Let's try it with the other mouse. Alright, that I can live with. So we've got this is my 3D graph. I'll explain why in a minute. Here's my, put me in the middle as well. Alright, so we've got graph here, graph here. Okay, we can see we've got quadratic with no roots. So I've clicked the real roots button here, and you can see it doesn't have any. I can move it around. Oh, wait, no, I can't. That's the program. Here you go. I can move it around a bit, so I can move it up and down. You can see when I put it below the axis, we got some roots. Okay. So, a way we can kind of show complex numbers and imaginary numbers is imagine them as in a separate dimension. And that might sound horrible, but it always helps me out picturing these things. So we're going to imagine that they exist in a dimension perpendicular to our kind of spatial dimension. So that's why I've got this 3D graph. So the 3D graph shows me the imaginary number line. Okay, I've called it I there. You can see I coming out screen towards us. So we've got Y in the obviously the Y direction. We've got X in the X direction. We've got I in the third dimension. Okay, we can only draw 3 dimensions. I've only put one set of imaginary because we would have imaginary Y's possibly as well. But for this purpose, we've got imaginary in the X and the I direction. Now, up until a few hundred years ago, and up until today for you guys, as far as you knew, that's what a quadratic looks like. And it is in the real kind of plane, in the real dimension, in the real plane, with real numbers. That's what a quadratic looks like. When we bring in complex numbers, because obviously we can use the same function, this one is obviously y equals x squared plus 2.1 in this case. You could put imaginary numbers into there too. So you could put the square root of -1 in. So let's imagine we do that. Imagine. If we put in the square root of -1, I'm just going to bring I'll just bring the iPad back, because it might be sort of right. So that'll do. So I'll bring the iPad back just so I can do some writing down here. We've got x squared plus 2.1. That's the graph that I've drawn above us. Which I can't seem to move, weirdly. It's locked. Cool. I'm going to keep it locked actually. Alright, let's do that. Okay, so we said x squared plus 2.1. Okay, so all your lives, and mathematicians up till a couple hundred years ago had only ever tried putting numbers in. Yeah, positives, negatives, fractions, whatever. Put them in, plot the graph, that's what we get. We can also put in complex numbers. So we could put in I. What if x equals I? So sub in I. Remember, I is the root of minus 1. So if I put the root of minus 1 in, and square it, and plus 2.1, well, the root of minus 1 squared is minus 1, plus 2.1 gives me 1.1. Oh. So when we put in a complex number, we get a y value. Interesting. So for every complex number, well, for most complex numbers, we can put them in, square it, we can now get y values in that third complex dimension. And this is where our roots are coming from. When y is 0, there's not a real solution, there's an imaginary solution. So I'm going to plot this. We're going to look at, we'll look at this one first of all. So this currently has no roots. If we quickly try to solve this for when it has roots, might make it slightly easier actually. Let's do it. Oh. Let's make it x squared plus 4, I think, will be a lot easier to solve with algebra. So I've drawn it there. X squared plus 4 equals 0. Let's take 4 each side. X squared equals minus 4. So x is plus or minus root minus 4. The root of negative 4, well, we can do what we did earlier and say x is plus or minus 2i in this case. So this should cross the axis at 2i. So we're going to draw this in my other sketch, my 3D sketch up here. I'm going to show you what a quadratic actually looks like. Ready for this? So this is what a quadratic actually looks like when we consider the imaginary dimension, the imaginary plane as well. Alright, my thing is horribly zoomed in. I'm going to try and see if I can recenter it. This is a quadratic. So you can see the bit that you guys knew is there in red, still there looking like a quadratic, but it's got this weird kind of spill into the imaginary dimension. So you can see I said if we solve this, this is why this one doesn't work very well. You can see my roots don't quite match up with the curve. If we zoom in, you can see my solutions are at plus or minus 2i. Again, you can see for some reason I couldn't get this to center properly. I don't know what, I stole this off the internet. So whoever did this programmed it wrong. I tried, but I couldn't quite fix it. Where's the, so I'm just going to bring myself above the graph. So yeah, this should be centered. And then we get our roots in the right place. I tried last night, but I couldn't be bothered. You guys can kind of work out what it looks like. It doesn't look like a big Pringle yet. Anyway, so that's where our roots come in, because you can see that is the moment where this curve crosses the where we get y equals 0. Y equals 0 there, bam, at those 2 points, 2y and minus 2i. Anyway, so we can look at the one we did earlier. So if I just put that down here a sec. If we go back to the one we were looking at as a question earlier on today, which was, what was it again? X squared plus 2x plus 5. So we solved that and we said it was x. So let's do it here, x squared plus 2x plus 5. We got x is minus 1 plus 2i, and x is minus 1 minus 2i. So we've got complex numbers. Okay, so let's see if we can draw this. So I'm going to move my quadratic. So I'll move b up to 2, and c was 5. So there you go. You can see on the left sketch, we've got my, it's a quadratic. You can see it's moved slightly. If I zoom in on there, you can see where the minimum point is. As you would expect, the minimum point is at 4, 1. There you go. And then we can draw our complex version of this. Up here, sorry guys, we've got like 6 windows open. And you can see, yeah, it's again, it's got the same problem, it's not spilling out quite right. But yeah, we can see we've got our complex roots, because they're complex this time. They have a value of 1, -1 in the x direction, as you can see down here, -1. X is -1, that's the real part, and then -2 is the imaginary part, which you can see in the imaginary plane, to plus or minus 2i, and then -1 in the real plane. I'll zoom out a bit more, you can kind of see. There it is. Cool, right, I mean this isn't completely accurate because I can't put in imaginary y values, but from the look of this equation, because we got an x squared, you'd square it, it's going to get rid of any imaginary values anyway. So in this case, we don't need to see the imaginary y values. With a cubic, we might though. So yeah, but for this case, you can kind of just to give you guys a picture. It does still cross the axis, but it's not in the real number plane. You guys know it's in the imaginary number plane, which we can kind of draw as a third dimension. And we'll be doing a bit more of this in a few weeks' time. There's a specific type of diagram that lets us represent complex numbers. But yeah, that's what a quadratic actually looks like. Right, I'm going to get rid of this. Does anyone have any questions? If an equation has real roots, does it also have imaginary roots? That's a very good question. It can, depending on the type of question. So, a quadratic has 2 roots. Quadratic, I'm not really ready for this, but may as well talk about it now. So yeah, a quadratic must have 2 roots. All quadratics have 2 roots. So quadratic. It could have 2 real or 2 imaginary or 2 complex. But it only has 2 roots total, or it could have a repeated, repeated real, repeated imaginary, repeated complex. Yeah, a cubic could have 2 real. No good. Cubic could have 3 real. It could have 2 imaginary plus 1 real, or obviously 2 complex plus 1 real. You always have your complex numbers in sets of 2 because, well, for non-complex functions, you can have complex functions as well. For non-complex functions, when you times it all out, it needs to become real again. So if an equation, so it can have a mix of real and imaginary, but if it has imaginary roots, it always has an even number, so they cancel out if it's a real function. If it's an imaginary function, it could have different numbers of imaginary roots. Quadratic can't have 1 real and 1 complex. No, unless it's a complex quadratic, and then possibly. What does a repeated imaginary root look like? Wait, could we have a repeated imaginary root? I just kind of said that, and I thought straight afterwards. Could we have that? I think we probably couldn't. No, we couldn't, because it wouldn't cancel out properly. It would still be complex. Yeah, we couldn't have a repeated imaginary root, because if you tried squaring it out, it wouldn't turn real. You'd get a non-real term in the middle. You're going to see this later on today when we start multiplying things. You can imagine, when we were rationalizing denominators with surds, and we times it by, we changed the sign in the middle and times them together so that it would cancel out the last term and the middle terms would add and disappear. It's the same kind of thing with complex numbers. Because we're talking, root of -1. To turn it real, You've got to have root minus 1 times root minus 1 in order to square it and just get a minus 1. So no, you couldn't have a repeated root because it wouldn't be real. Okay, anyway, well, come on, guys, asking me some good stuff so far. We can take time on this because, as I said, we don't have too much to get through this week because it's a new topic. We want you guys to be comfortable with how weird it is. All right, here we go. So, what Gauss said then? Gauss said a few things on the topic. He first said, we must admit with humility that while number is purely a product of our minds, space is a reality outside our minds. I've typoed this. So that we cannot completely prescribe its properties in the same way. So he's saying we can't deal with space and number in the same way because space exists outside our minds. Number is something purely invented by the human brain. I mean, you can argue with that, but he went on to say that this subject, so complex numbers and imaginary numbers, has been surrounded by mysterious obscurity. It's because of an ill-adapted notation. So he says, because we called them imaginary numbers, and then we went on to call them complex numbers, we've alienated people straight away. The second we say imaginary numbers, you guys, I mean, what was the first question? Jen said, what's the point of them? What's the point of them? They're imaginary, they're not real. They're imaginary, or there's the side, they're complex, they're too hard for me to understand. Gauss was saying both those points are stupid. They're ill-adapted notation. Why do we use I? If we didn't use I, we could have made it all right. So Gauss kind of proposed, for example, plus 1, minus 1, the root of minus 1. If we'd call them direct, inverse, and lateral, instead of positive, negative, imaginary, or impossible, people wouldn't have been so alienated by them in the first place. I just had a knock at the door. I'll be right back. See if you guys can think of any questions while I go check what that is. It's got some posts. That's exciting. So, yeah, Gauss argues why if we hadn't called them imaginary, if we hadn't called them complex, people would understand it more. So yeah, positive, negative, fine. We can deal with those fine. Imaginary, what? I mean, and it's the same as before. I mean, negative numbers up until a few hundred years ago, no one knew what a negative was. No one could understand negatives. Yes, we had things like debt, but we didn't have kind of multiplying negatives and dividing negatives and squaring them. You guys, you're kind of standing on the shoulders of giants, so you can understand all these complex mathematical ideas that people couldn't comprehend years ago. Imaginary numbers up to a couple hundred years ago, no one knew what they were. Pythagoras would have blown his mind. So yeah, it probably seems weird at first to you guys, but it's just because we're introducing something new. I mean, look at the Greeks and the Romans. They couldn't comprehend zero, couldn't comprehend a negative. No, we don't want to know about it. But imaginary is kind of like the final piece of the jigsaw puzzle. That is number kind of completed. So, yeah, so we're going to be using these quite a lot in further maths. There's a good few topics that use them. Try not to think of them as imaginary. That is just a word. It's a word we could have used, as Gauss said, we could use lateral. They are lateral numbers. They are numbers perpendicular to the plane of numbers we're used to. They're not really imagined. They're not part of our imagination. They do exist. They come up in real life. Strange places, but they do pop up. So complex roots are tangible things. You see in a lot of as I studied physics, and I do like maths. Maths is good. But yeah, from my physics background, you get complex roots to physics equations that describe how the world works, how quantum mechanics works. So some of these crazy obscure engineering, mathematics, fluid flow, quantum dynamics, all this stuff has complex numbers at the heart of it. So they are intrinsic. You could argue all numbers are made by humans. We're just prescribing them to our problems, but they've got us pretty far. They've been pretty useful so far. Anyway, so we're going to try. What was I doing here? I think that was my timeline. Anyway, so we're going to try and get used to these. We're going to start slow, and what I want you guys to do is to simplify some imaginary numbers. So we'll do an example, the EG1. Simplify square root minus 36. So I'm going to use surds for this. I'm going to say this is the same as the square root of 36 times the square root of minus 1. Square root of 36 is 6. This is 6 root minus 1. In other words, this is 6i. There you go. Can do another one. EG2. So we got root of minus 28, which we can say is minus root 1, root 28. 28 is, we can split that up into root 4, root 7, root minus 1, which is 2 root 7 I. And the reason we write it like this is we don't want to confuse it and include the I with the root 7. We want those to be separate. Cool, alright, so you guys are going to try some of these. I'm going to open my post. It's going to be very exciting. So can you guys simplify root minus 49, root minus 45, and root minus 200. I'll check back in 5 minutes to see how you got on. Cool. Right, how do you guys get on? Don't forget to comment your answers as you do them, just so I can check how you've got on. But let's go through these. So, minus root 49. Well, we can turn that into 49 minus 1, so that's going to be 7i. 45, we could turn into root 9, root 5, root minus 1. So that's going to be 3 root 5i. And root 200, we could turn it into root minus 1, root 2, root 100. So that's going to be 10 root 2 i. It's really tempting to underline them because of vectors, but they're not vectors, so try not to underline them. They do behave a bit like vectors, as you'll see. Alright, what else have we got to do today? Not much more, to be honest. Cool. Right, so we need to look at arithmetic. So, how's this? Would you write it as 3i root 5 or 3 root 5i? But I at the end, normally. 3 root 5i. Yeah. Okay, so adding. As I said, similar to vectors. So if we want to add complex numbers, we can do 10 plus 3i, take 7 minus 3i, and we take away the real. I said adding and then written subtraction. Adding and subtracting are the same thing. Subtract or adding complex numbers. We add the real parts and we add the complex parts. So we get 10 minus 7 is 3, and 3 minus 3 is going to be 6. So 3 plus 6i would be the answer to that one. Let's get you guys doing some of these then. So if you guys could do these and write your answers. George, what are you saying? So if you guys could try 1, 2, 3. Yeah, if you guys could try these 3, that would be awesome. So 4 minutes. Give it a go. Right, that'll do. These are pretty easy, so let's do them. So for the first one, add the reals, add the imaginary, so 13 plus 11i. For the next one, 3 root 2 take root 2 is 2 root 2. I minus minus I is going to be plus 2i. And the last one, minus 2 plus 1 is minus 1, plus 12 is going to be 11. And then minus 7 plus 3 is minus 4. Take 1 is minus 5i. There you go, nice. All right, next up, multiplication. We might finish early today. Multiplication, at the moment, we're only going to do real times complex. We're not going to do complex numbers times complex numbers, but we will next week. Yeah, I'm going to have to go do something in a sec. So, for example, real times complex. We will do complex times complex though. To do real times complex, it's going to be, imagine 5 times 3 plus 6i. If I times those together, we'll get 15 plus 30i. So just times them as you would expect. All right, so I'm going to get you guys to try some of these. So, question 1. Right, if you guys could try those ones. We'll say 5 minutes. Cool, give them a go. Right, guys, let's go through these then. So first one, we're going to get intermediate. Well, let's just do it. 6 plus 6 is 12, and then 2i plus 3i is 5i. Next one is going to be 3 plus 5i. Next one is going to be, what's that going to be? Minus 2, minus 7 over 2, minus 5.5 minus 11 over 2. And 3 over 4 plus 1 is going to be 7 over 4. I check these because I'm doing it quite fast. The last one, 20 minus 20 plus 4 is 24. And then 15, take 8, 7, I think. For those. Let me know if I'm wrong, but I think that's it. Alright, and last couple questions for you guys is to rationalize these. And then to find so you guys can do those. I'll give you 10 minutes to do that. I lost my timer now. There you go. And we'll go through these right before the end. So see how you get on. That's all we're going to do today. So yeah, it starts off easy. It does get harder, but we're taking it slow, like I said. Alright, cheers guys. All right, cool, let's do it. So rationalizing denominators, remember we times it by root 2 over root 2. So we'd get 4 root 2 minus 2 root 2 I over 2. So we get 2 root 2 minus root 2 I. First one. Second one times it by the sign changed version. I can't remember what it's called now. 1 minus root 3 over 1 minus root 3. So we got times all out. Yeah, I got that. So we get 2. This is going to take forever, isn't it? Okay, 2 minus 6i minus 2 root 3 plus 6 root 3i all over 1 minus 3. So I get 2 take 2 root 3 minus 6i plus 6 root 3i, so I'm going to say that's plus 6 root 3 minus 6i over minus 2. So I can divide all that by minus 2. Run out of space, let's put it on top instead. So we're going to get minus 1 plus root 3 minus, I guess, 3 root 3 minus 3 I. That one. Last bit. So we are trying to find z take w and w plus z. Z take w, 7 minus 6i minus 7 plus 6i. We're going to get the 7, take the 7. We're just going to cancel. We get minus 6i, so we can be minus 12i for that one. W plus z, we are going to get 14 for that one. So this one is totally imaginary. This one is totally real. We'll talk more about that tomorrow. Cool, thank you guys. I gotta go. I gotta do some stuff, but I will speak to you tomorrow. Any other questions on this? Email or wait till tomorrow. Cheers, guys.